Imagine a world, maybe not so far off, where the unexpected is, well, kind of the norm. Think about a self-driving car, right? It needs to track a child darting into a crowded street like instantaneously and predict their path even if the sensors are partly blocked or the data's fuzzy.
Yeah, or picture a drone flying through a city, navigating all these buildings. It has to maybe dodge some unmapped crane or something while delivering a package, and it needs to react in, like, milliseconds.
Exactly. So how do these intelligent systems make these critical decisions, in real time, especially when the information they're getting is often noisy or incomplete or just uncertain? It's a massive challenge.
It really is a fundamental one for any system we want to call truly autonomous.
So today on the deep dive, we're going right into the heart of that challenge. We're talking about probabilistic models, specifically these really powerful tools called Bayesian systems.
Ah, yes, Bayesian methods. They're incredible tools for making sense of exactly that kind of uncertain data.
They really are. They're like the mathematical backbone helping these machines understand the world, predict what might happen next, and, act accordingly. But there's a catch, isn't there?
There always is, and it's a big one.
These models are, well, notoriously computationally expensive. That's the term people use.
Which basically means they often struggle to run fast enough for real-time stuff, especially on smaller, energy-efficient hardware. The kind you need right at the edge, as they say.
Right, on the device itself. So our mission in this deep dive is to unpack a really novel, I think quite ingenious approach to tackle this exact problem.
Yeah, we're looking at a paper that proposes a very clever, almost elegant way to put these complex Bayesian models directly onto specialized hardware.
And not just any hardware, something called Field-Programmable Gate Arrays, or FPGAs.
Using a technique called stochastic computation.
Okay, let's unpack this then, because this isn't just about making things a bit faster, is it? It feels like a real shift in how we process information.
I think so. It could genuinely pave the way for a whole new wave of real-time edge computing applications.
We're talking about a future where that sophisticated intelligence lives right on the device, right, on the car, the drone, that smart sensor.
Without constantly needing to phone home to some powerful cloud server miles away.
It's pretty exciting how something that sounds complex can be made, well, surprisingly simple and super efficient. Opens up a lot of doors.
Definitely.
So let's start at the beginning. The basic challenge. We've said Bayesian models are powerful, but why are they so tricky for hardware? You might not even realize it, but these Bayesian systems are kind of humming away quietly behind the scenes in a lot of the tech around us.
Oh, absolutely. They're the unsung heroes in many cases. What's really fascinating when you look at the source material is just how broadly they're used. Think object tracking, for instance. That's absolutely vital for self-driving cars to keep tabs on other vehicles, cyclists, pedestrians.
Predicting where they're going in busy traffic.
Exactly. And then there's SLAM simultaneous localization and mapping.
Right, that's how a robot, maybe in a warehouse or exploring a new place, builds a map while figuring out exactly where it is on that map it's building.
Precisely. And even the inertial navigation systems in, your phone or your smartwatch. They use Bayesian ideas to fuse data from accelerometers and gyroscopes to figure out how you're moving your orientation.
Ah, okay.
They're just excellent at what's generally called state estimation.
So state estimation, just to make sure we're clear for everyone listening, that would be like constantly figuring out a car's exact speed position, maybe even which way it's pointing, even if the camera feed is a bit blurry because of rain or the radar signal is noisy.
That's a perfect way to put it.
It's like getting the best possible guess about reality from this constant stream of imperfect data.
Exactly. You're constantly refining your belief about the current state, the state of the car, the state of the environment,
Yeah.
even when your observations are ambiguous or noisy.
And that's why they're so valuable, this ability to handle uncertainty.
Yes, and to fuse different types of messy data together. It provides a really solid mathematical framework for learning and making decisions when things are unpredictable. It's not just navigation either. You see it in predictive maintenance, guessing the state of a machine to predict failure.
Or even in medicine, maybe. Estimating a patient's condition based on various tests.
Precisely. The applications are incredibly broad.
Okay, so if they're so great, so versatile, why aren't they just everywhere, running on every smart device? Why isn't my toaster running a Bayesian model? Well, maybe not the toaster, but you know what I mean. What's the bottleneck?
Yeah, that's the multi-million-dollar question, isn't it?
Yeah.
And it leads right back to that computational complexity issue. Bayesian calculations, especially for continuous probabilities, often involve really complex math.
Like integrals and matrix stuff.
Exactly. Integrals, matrix inversions, constant normalization steps, all things that chew up a lot of processing power and time. If you try to run these models in real time using standard software on a typical CPU, like in your laptop,
It just can't keep up.
for many applications that need instant responses, no, it's just too slow. They demand huge amounts of processing, making real-time decisions a massive hurdle. And you can't have a self-driving car taking seconds to decide what to do.
No, definitely not. Milliseconds matter there.
Absolutely. And this computational load really restricts where you can deploy them, especially in edge computing.
Those small devices, limited power.
Right. Small robots, battery-powered drones, tiny IoT sensors. They can't always just beam all their data to the cloud because of latency or bandwidth limits, or simply because it uses too much power.
They need to think for themselves right there on the spot.
Exactly. Process locally, decide locally. And often, designers have had to settle for simpler, maybe less accurate algorithms just to get the speed they need. It's a trade-off.
But it's not like people haven't tried building specific hardware for this, right? This problem must have been known for a while.
Oh, absolutely. It's a long-standing challenge. The paper mentions some earlier attempts. For example, researchers like Vigoda and Chaparro looked into using analog VLSI circuits.
Analog, like old school electronics.
Well, analog has its strengths,
Yeah.
particularly power efficiency for certain tasks. But for complex, adaptable Bayesian systems, they have big drawbacks.
Like what?
They're really hard to scale up for large, complex problems. And imagine trying to reprogram a massive analog circuit if you change your model or your sensors.
Nightmare.
It's a huge undertaking. Very complex design, complex testing, totally different from the standard digital design flows we use now. They're just not very flexible, not programmable in the way we need.
Okay, so analog was maybe a dead end for this specific problem. What about standard digital circuits, the ones in all our computers?
That's the more common approach, obviously. But even there, trying to implement inherently probabilistic Bayesian models on deterministic digital circuits, it creates inefficiencies.
How so? Digital seems precise.
It is precise. Digital circuits are built for exact calculations. Zeros and ones mean absolute things. They aren't inherently designed for the randomness and probabilities that are core to Bayesian thinking.
So it's like trying to fit a round peg in a square hole.
That's a great analogy.
Mhm.
You end up simulating probabilities using fixed-point numbers, needing complex multipliers, division circuits, random number generators, all of which take up a lot of chip area and burn power.
The architecture just isn't naturally suited for it.
Exactly. It leads to bigger chips, high hour power consumption, and often still not the real-time speed you need for complex models.
So we've got these powerful Bayesian models we need, but they're too slow for the edge, and the hardware approaches tried so far haven't been efficient enough. It really does sound like we need a totally different approach.
And that's where this paper gets really interesting.
Right, this is the part that made me sit up. The paper proposes this different paradigm. Stochastic computation, or SC, it sounds complex. Stochastic computation.
The name is a bit intimidating, I agree.
But the core idea, you said, is surprisingly simple.
It really is, once you get the concept. And SC isn't actually brand new. A researcher named B.R. Gaines suggested it way back in 1967.
Wow, 1967. Why haven't we heard more about it?
Well, back then, the hardware landscape was different, computational needs were different, deterministic digital computing was king, and the specific kinds of problems where SC really shines, like edge AI and complex probabilistic tasks, weren't as widespread.
But now they are.
Exactly. Now, with AI everywhere, especially at the edge, SC is having a real comeback.
So what's the fundamental idea? How does it work?
Okay, the key shift is how you represent numbers. Forget fixed binary strings like a 0, 1, 1. In SC, you represent a value as a bit stream, a sequence of ones and zeros flowing over time.
A stream of bits, how does that hold a value?
The value isn't in the specific pattern. It's in the probability of any given bit in that stream being a 1.
The probability. Okay, hang on. Give me an analogy.
Think of a light bulb flickering randomly. If it's on a 1 50% of the time over, say, a second, that stream represents the value 0.5 if it flickers on 90% of the time.
It represents 0.9.
Exactly. More ones in the stream means a higher probability, a higher value. The individual bits are random, but the overall proportion of ones carries the number.
Huh. So it's an inherently probabilistic way to encode numbers.
Precisely, which you can see aligns beautifully with Bayesian methods that are all about probabilities.
Okay, I think I get that. But this is the mind-blowing part for me. The paper says you can do complex math like multiplication with simple logic gates using these streams. How on earth does that work? It feels like breaking the rules of digital logic.
Haha. It feels like it, but it's just very clever engineering. Let's take multiplication, which, as we said, is costly in normal digital circuits.
Needs complex multiplier circuits, lots of gates.
Right. But in SQA, if you have two independent bit streams representing probabilities PA and PB,
Sure.
you can multiply them using just a single A and D gate.
One and D gate.
Seriously, think about it. An A and D gate only outputs a 1 if both input A and input B are 1, right?
Right.
So if the probability of input A being 1 is PA, and the probability of input B being 1 is PB, and they're independent, the probability of the A and D gate's output being 1 is exactly
Good A
correct.
times P.
PA times PB. Multiplication with one simple gate. It's incredibly elegant.
Wow. Okay, that is clever. What about other operations, like addition?
Addition is a bit trickier, but still very efficient compared to standard adders. You can approximate it with an OR gate, or do it more accurately with circuits involving things like multiplexers and counters. This is still much smaller than traditional hardware.
So the core idea is leveraging the statistics of the streams.
Yes, it operates on probabilities directly. And that's why it's so perfect for probabilistic algorithms like Bayesian models.
And the benefits are?
Huge. Drastically lower hardware area because the gates are so simple, much lower power consumption. Plus, it's inherently fault-tolerant. A few flipped bits in the stream don't drastically change the overall probability.
Which is great for noisy environments or less reliable hardware.
Exactly, and crucially for speed. Because these operations are so simple and small, you can do tons of them in parallel. Massive parallelism.
Which means lots of calculations happening at the same time, speeding everything up.
Dramatically. All these factors, low area, low power, parallelism, are exactly what you need for real-time edge computing.
So this isn't just a neat trick they use for this one specific source localization problem then. It sounds more fundamental.
That's absolutely the point and why this is potentially so impactful. The underlying math of Bayesian systems, combining priors with likelihoods, normalizing it's broadly similar across many different applications.
Whether you're tracking an object or diagnosing a disease.
Right. The core computational structure is often the same. So this SC design they've built isn't just for finding light sources. It acts like a potential building block.
A reusable component.
Exactly. A modular, reusable piece that designers could potentially adapt to implement many other complex Bayesian models relatively easily.
That's huge for designers. Instead of reinventing the wheel for every probabilistic task.
They could potentially leverage these SC-based modules. It could massively speed up the design process for creating versatile, scalable hardware for all sorts of AI and probabilistic tasks.
Real-time inference on sensor networks, smarter robots, better medical devices.
All running efficiently right there at the edge, not needing the cloud. It could really democratize access to quite sophisticated AI capabilities.
Okay, let's make this more concrete then. The paper uses this SC approach for a specific problem. Source localization. What source are they trying to locate and why pick that problem?
Right, so to prove the concept works, they tackle the problem of estimating the position of a source in real time, specifically in a noisy environment, using their proposed hardware.
And the source is?
For the experiment, they use an omnidirectional light source, something that emits light equally in all directions. It's a good general test case.
And how is this relevant to us, the listeners? Where would we see source localization being used?
Oh, in lots of places.
Yeah.
Think of a robot in a factory finding its charging station, which might have a little light beacon on it.
Yeah.
Or navigating to a specific workstation emitting a signal.
Okay, yeah.
Or maybe emergency responders trying to pinpoint a distress signal inside a collapsed building. Or a drone looking for a lost hiker by triangulating their phone signal.
Even in smart homes, locating pets or people.
Potentially, yes. For intelligent lighting or climate control. Anytime you need to find where something is based on signals it emits, especially when there's interference, this kind of Bayesian source localization model, or BSLM, is really useful.
So the paper describes their experimental setup, Figure 1. Can you walk us through that? It sounds like a little robot arena.
It is, basically. Imagine a flat, square area like a floor. They divide this conceptually into a grid, say K by K squares. For their tests, it was 40 by 40.
So 1,600 possible locations for the light source?
Exactly. The light source is assumed to be in one of those grid squares. Then you have the UGV, the unmanned ground vehicle, their little robot moving around on this grid.
And how does it sense the light?
It has an array of 8 photodiodes on top, simple light sensors. Each one covers a 45-degree sector around the robot, so together they give 360-degree coverage.
Ah, like pie slices all around it.
Precisely. So it can kind of triangulate where light is coming from, dividing its surroundings into these 8 sectors. When a photodiode detects enough light, it outputs a 1, otherwise a 0.
Are there any simplifying assumptions they make for this test?
Yes, a couple important ones for this proof of concept. They assume there's only one light source in the arena, and the robot's movement is restricted to 45-degree angles, which lines up nicely with the sensor sectors.
Okay. Simplifies the math a bit, but still tests the core idea.
Exactly. It still demonstrates the Bayesian inference and the SC hardware effectively.
But you mentioned a noisy environment. Real life isn't clean. How does the model handle noise, reflections, other lights?
Right, and this is crucial. That's where the Bayesian approach really proves its worth. The paper explicitly accounts for things like reflective surfaces or stray ambient light acting as distractors.
That cause false readings.
Exactly. They quantify this with the probability of noise, which they call Pn equals B beta. So a photodiode might wrongly signal 1 even if the source isn't in its sector, just due to noise, or it might miss the source sometimes.
So how do they factor ELMA and the sensor's own accuracy into the calculation?
They defined a couple of key probabilities. First, ELMA alpha is the probability that a sensor correctly detects the source if it is present in its sector. Think of it as the sensor's reliability.
Okay, so high alpha is good.
Right. Then using alpha and beta, they derive these crucial likelihood functions. They call them L1K and L1K. L1K is the likelihood of getting the current sensor reading if the source is truly in grid K. LK is the likelihood of the reading if the source is not in grid K.
So basically, how likely is what I'm seeing given these two possibilities?
Precisely. These likelihoods quantify the evidence provided by the noisy sensor reading. They use ion bomb to calculate these likelihoods, effectively telling the system how much to trust or distrust each sensor reading based on the known noise levels and sensor accuracy. These likelihoods are the core pieces of evidence used in the Bayesian update.
Okay, so the robot knows its position. It has these noisy sensor readings, the zeros and ones from the photodiodes, and it has these likelihoods based on alpha and beta. How does it combine all that to actually figure out where the light source is?
That's the magic of Bayes' theorem implemented in their BSLM. The goal is to calculate the posterior probability for every single grid square.
Posterior probability, meaning the probability after considering the latest sensor reading.
Exactly. It's the updated belief. For each grid square, the ZRL, the system calculates what's the probability the source is in this specific square, given the measurements I just took.
And how does it calculate that?
It uses Bayes' theorem, which essentially combines the prior probability, what the system believed about that square before the measurement.
Its previous best guess.
Right. It combines that prior belief with the likelihood we just talked about, how likely the current measurement was if the source was or wasn't in that square. It elegantly balances old beliefs with new evidence.
And it does this for all 1,600 squares.
Yes, and it does it repeatedly over time. It's not a one-shot deal. As the UGV moves and gets new sensor readings at each time step, it recursively updates the posterior probability for every single grid square.
Constantly refining its belief map.
Exactly. You can see this in pseudocode 1 in the paper. It iterates, updating the probabilities across the whole grid. The grid square that ends up with the highest posterior probability after an update is then declared the system's current best estimate of the source location.
This constant updating and refining based on new data, that's really the essence of intelligent learning in uncertain situations, isn't it?
It absolutely is. It's how these systems adapt and make sense of a dynamic world, turning messy data into a coherent picture. Okay, theory makes sense. BSLM makes sense. Now the hardware. How did they actually build this on an FPGA using stochastic computation? Walk us through that architecture.
All right, Figure 2 shows the top-level view, and it's designed around that massive parallelism we talked about. Since there are KX, grid locations, they don't calculate sequentially. They instantiate KX, K-parallel inference paths.
So 1,600 mini calculators running simultaneously.
Pretty much. Each path is dedicated to one specific grid square. Its only job is to calculate and update the probability that the source is in its assigned square.
That's how they get the speed.
Absolutely. And each of these parallel paths has 3 main components inside it.
Okay, what are they?
There's a triangulation module, then the core stochastic Bayesian module, and finally a register to hold the probability value from the previous time step.
And all these paths feed into something at the end.
Yes, all KXK paths feed their calculated posterior probability into a final block called the max module.
Let's take those modules one by one. First, the triangulation module in each path. What does it do? It's all the geometry? It is, basically. Its job is to figure out the spatial relationship. For the specific grid square that this path is responsible for, it calculates. Which of the UGV's 8 sensor sectors does this square fall into, given the UGV's current position and heading?
Ah, so it connects the grid location to a specific sensor.
Exactly. It takes the UGV's position, the grid's position, and all 8 photodiode readings. If it determines, say, that grid 1025 is currently in sector 2 relative to the UGV, it selects the reading from photodiode 2, Z2, and passes that specific reading to the stochastic Bayesian module for this path.
Got it. It filters the sensor data relevant for its specific grid square.
Precisely. It translates physical location to the right sensor input for the Bayesian update.
Okay, then the crucial part. The stochastic Bayesian module. This is where the SC magic happens, implementing that Bayesian equation with bit streams.
This is absolutely the core innovation. This module takes the prior probability from the register and the selected sensor reading from the triangulation module and performs the entire recursive Bayesian update, equation 4, using stochastic computation.
Including those tricky division and normalization steps.
Yes. Operations that are usually bottlenecks in digital hardware are handled efficiently here, using simple stochastic logic.
So how does it start? It needs to get those bit streams first, right? Using the SNGs?
Correct. The very first step inside this module is converting the necessary numbers into stochastic bit streams.
Which numbers?
The key probabilities we defined earlier, sensor accuracy and for noise probability, and also the prior probability for this grid square, read from the register PT1. These are likely stored as standard binary numbers initially.
Okay. And how does the stochastic number generator, SNG, do the conversion? You mentioned it before.
Right. Figure 3 shows the idea. The SNG takes a standard binary input, like an 8-bit number representing 0.8 for alpha. It then uses a circuit called a linear feedback shift register, LFSR, to generate a sequence of pseudo-random numbers.
Random numbers?
Yeah.
Okay.
In each clock cycle, it compares the random number from the LFSR to the binary input number. If the random number is less than or equal to the input number, the SNG outputs a 1. Otherwise, it outputs a 0.
So if the input number is high, like 0.8, the random number is likely to be smaller, so you get more ones.
Exactly. The proportion of ones in the output stream over time statistically matches the value of the input binary number. It's like using the input number to bias a random coin flip generator.
Clever. Okay, so now we have stochastic streams for alpha, beta, and the prior probability. What next inside the Bayesian module?
Next comes the likelihood and normalization circuit, shown in figure 4. This takes those streams and does the math.
How does it calculate the likelihoods, L1K and L0K?
It uses a likelihood module. This behaves a lot like a multiplexer, a digital switch. The actual sensor reading for this sector, either 0 or 1, acts as the control signal.
So the sensor reading chooses which probability stream to use?
Essentially, yes. It selects the appropriate stochastic likelihood based on whether light was detected or not, using the US and VIS streams. The S just means stochastic stream. And remember, calculating one probability is easy. Just invert the stream with a NOT key gate.
Okay, likelihoods calculated stochastically, then the multiplication.
Simple. The likelihood stream is multiplied by the prior probability stream, PT1s, using just an A and D gate. Again, super efficient.
Right, the A and D gate trick that gives the numerator parts of the Bayes equation.
Exactly. You get 2 intermediate stochastic streams from these multiplications. Now the final challenge, the normalization, the division.
How do they divide using bit streams?
They use a normalization module. This is a really neat part. It uses a counter circuit, but one with both excitatory, add, and inhibitory, subtract block, inputs, driven by the intermediate probability streams.
A counter doing division.
Effectively, yes. The counter integrates the signals from the streams over time. Due to the way it's connected, its output value naturally settles or converges at equilibrium to the correct normalized posterior probability, P1 plus P2. It performs the division inherent in Bayes' theorem stochastically.
Wow, that avoids needing a complex digital divider circuit.
Precisely. And the final output of this counter is the updated posterior probability, PIT, provided as a standard 8-bit binary value ready to be stored in the register for the next time step. It converts back from stochastic to binary at the end.
Okay, so each of the 1,600 parallel paths does all of this triangulation, SNG conversion, likelihood, stochastic multiplication, stochastic normalization, spits out an 8-bit posterior probability for its assigned grid square. What happens then?
All those 1,600 probability values pour into the final module, the max module.
And its job is just to find the biggest one.
Exactly that. It searches through all the calculated posterior probabilities and identifies the grid square that has the highest value.
The location the system is most confident about.
Yes. The coordinates of that winning grid square are then output as the final estimated source position, x's.
How does it find the maximum efficiently with so many inputs?
They use a tree structure of digital comparators. Think of it like a tournament. Pairs of probabilities are compared, the winner moves on to the next round, compared against another winner, and so on. It very quickly funnels down to the single maximum value.
Ensures finding the max doesn't become a bottleneck itself.
Right. Keeps the whole process fast in real time.
Okay, the architecture sounds incredibly elegant and well-suited for the problem. But the proof is in the pudding. How did it actually perform? What did the experiments show?
And this is where it gets really exciting. First, they validated the whole algorithm in MATLAB simulation. They used that 40 by 40 grid, set alpha to 0.8 and beta to 0.4, so reasonably reliable sensors, but significant noise.
And did the simulation work?
Yes, perfectly. Figure 5 shows it nicely. You see the robot moving, and the probability map gradually focusing in on the true source location. It successfully localized the source in about 30 time steps in the simulation. So the underlying BSLM logic was sound.
But the key was getting it onto the hardware.
Absolutely. They then took that exact model and implemented it using Verilog, a hardware description language, targeting a real FPGA, a Zinc Ultrascale plus NIC.
And did the hardware match the simulation?
It did. The FPGA results accurately mirrored the software simulations, which is a crucial validation. It proved their stochastic computation approach worked correctly in actual silicon. They did use 8-bit fixed-point numbers internally for efficiency.
Which might cause tiny precision differences.
Exactly. And that, along with the inherent randomness of SC, is why the FPGA sometimes took slightly more time steps to converge than MATLAB. For instance, with beta at 0.6, more noise, the FPGA took 37 steps versus 30 in MATLAB.
Okay, a few extra steps, but what about the time per step? That's the big one.
That is the staggering difference. Look at Table 2. A single time step calculation in MATLAB running on a pretty beefy Intel Core i7 CPU took 0.22 seconds, 220 milliseconds.
Okay, noticeable lag.
Now, the SC implementation on the FPGA, running at a modest 100 MHz clock speed, achieved a latency per time step of just 20.66 microseconds.
Wait, microseconds, from 220 milliseconds down to 20 microseconds.
Yes. It's more than a 10,000 times speed up for a single step calculation.
That's insane. That's not just faster, it's practically instantaneous in comparison. That changes everything for real-time applications.
It absolutely transforms the feasibility. So when you look at the total time to actually find the source, including all the time steps, for that Baco 0.6 case, MATLAB took 6.6 seconds total.
Okay, still quite slow if you need an instant answer.
The FPGA was stochastic computation. It completed the entire localization in 0.76 milliseconds.
Milliseconds, not seconds. Less than 1 millisecond total time.
Exactly. From over 6 seconds down to under a millisecond. That's the kind of leap that makes real-time complex Bayesian inference possible on edge devices.
And was it efficient in terms of how much of the FPGA it used? Was it a resource hog?
Not at all. That's the other amazing part. Table I shows the resource utilization. It used only about 12.7% of the lookup tables, LUTs, the main logic resources, and just over 4% of the registers on the FPGA.
So tiny usage. Loads of space left over.
Loads of space. You could easily scale this up to a much larger grid, or add more complex features, or integrate other tasks onto the same chip without running out of resources or needing a much bigger power-hungry FPGA.
Wow. Fast and efficient.
The best combination. So the experimental results really provide strong evidence. They show this approach works, it's incredibly fast, and it's very resource efficient. It proves complex Bayesian computation can be done in real time on hardware using SCA.
So wrapping this up, what we've really seen today is just a brilliant solution to a genuinely difficult problem, right? This deep dive into Bayesian source localization showed how rethinking computation itself using stochastic computation unlocks performance we couldn't get before.
I think that's exactly right. By really leaning into the probabilistic nature of the models and using these simple logic gates on FPGAs in a clever way, they've built something that offers that massive parallelism and real-time speed that just wasn't practical with older methods, especially for edge devices.
And it feels like this has implications far beyond just finding a light source, as cool as that experiment is.
Oh, absolutely. This isn't just about localization. Because the architecture is modular and scalable, the principles can be adapted for many other Bayesian algorithms.
Like in robotics. Better navigation, maybe.
Definitely. More robust navigation, obstacle avoidance, even things like predictive maintenance on the robot itself. Imagine self-driving cars making even faster, more reliable decisions, especially in bad weather or complex scenes.
Or medical devices. Wearables analyzing health data in real time.
Yes, potentially analyzing sensor data right on the device for faster alerts or insights. Environmental monitoring, industrial automation for detecting faults instantly, the list goes on.
It really seems to enable that whole vision of edge AI, making smart decisions right where the data happens without the cloud delay.
Exactly. More privacy, less power, instant responses. That's the promise this kind of hardware architecture helps deliver.
It really makes you reconsider how we design smart devices for the future, challenges the old assumptions about what's possible on small hardware.
It really does. And maybe the provocative thought to leave with is this. If simple bit streams and basic logic gates can unlock such complex real-time decision-making, what other problems that seem computationally impossible today might become solvable if we just find a different, maybe more natural way to represent and process the
Or
information?
maybe we need to think less deterministically sometimes.
Perhaps. It suggests there's still so much innovation possible just by revisiting the fundamentals of computation. So, keep exploring, keep questioning, and definitely keep an eye on how these shifts in hardware design are quietly reshaping the intelligent world all around us.